Welcome back. This is video 2 of, well, I'm not sure how many there'll end up being. I'm working through 14 implicit differentiation examples. In example or video 1, I went in great detail to each of the steps and started with looking at these instructions of how to find y prime. That's another way of saying the derivative of y with respect to x. So what we'll do is use the chain rule to do the derivative of each term in an equation. And then the second step is to solve for that y prime. But this is the second video. If you need a little more assistance, and I'm going to encourage you to go back to that first video first. The format I'm going to use, even though I've been doing this for a while, I'm going to spread this out and physically write out that what I'm doing is a derivative with respect to x of each of these terms. Some of them are quite easy because the derivative with respect to x of 4x is just going to be 4. The derivative with respect to x of a constant 2 is just going to be 0. So those pieces are going to be somewhat easy. I'm going to have to pay a little more attention to this piece, because do you see what happens? We've got an xy cubed, or maybe think of it as a negative 4x times y, or maybe think of it as a negative 4 times xy cubed. Any way you look at it, we're going to have to apply the product rule, so that's going to involve a bit more. Same thing with the 2x cubed y cubed. We could think of it as 2 times the derivative with respect to x of this product of x cubed and y cubed. So those two pieces are going to take a little bit more. Let's jump in and get started here. So this easy one, the derivative with respect to x of 4x is just 4. And when I get to this negative 4xy cubed, I'm going to pull out that negative 4 and then say times the derivative of xy cubed. So notice how I'm going to be writing this. 4 equals negative 4 times. When I do the derivative of xy cubed, I'm going to be using this product rule. So we're going to have the derivative of x, which is 1, times the g, so times y cubed, plus the derivative, or times f, which is x, times the derivative of y cubed, which is 3y squared. But don't forget to chain, because then I have to do times y prime, right? Because when I do the derivative of x with respect to x, that's just 1. But the derivative of y with respect to x, I've got to remember to include the y prime, the chaining. Doing the same thing to this next example, this next term. I'm going to pull out the 2 again, because that just seems to make it quite a bit easier. And we're going to do minus 2 times the derivative of x cubed y cubed. Do you see how I pull out this negative 2? And when I do the derivative of x cubed y cubed, applying the product rule here, I'm going to get the derivative of the first, so the derivative of x cubed, 3x squared, times the second term, so times y cubed, plus the second term, or the first term, f, so times the x cubed times the derivative of the second, the derivative of y cubed. Here's where I've got a chain, right? So I've got 3y squared, and then remember to chain that y prime. Simplifying this just a little bit, I'm going to have 4 equals, when I distribute this 4 to both pieces here, I'm going to have negative 4y cubed. I'm distributing the 4 to x 3y squared y prime. Negative 4 times 3 is negative 12 x y squared. And then I've got this times y prime. I'm going to pull out every y prime as I go here carefully, because the next step is going to be to solve for y prime, right? Distribute this negative 2. Negative 2 times 3x squared y cubed is going to be negative 6 x squared y cubed plus negative 2 times 3 gives me minus 6 x cubed y squared, and then we've got our y prime. The next step, the last step, is to solve for y prime. So to solve for y prime, I'm going to subtract this negative 4y cubed from both sides and subtract the negative 6x squared y cubed from both sides. And here's what that's going to look like. We'd have 4 plus 4y cubed plus 6x squared y cubed, because when I add that to both sides, or subtract the negative from both sides, when it moves over to the other side, remember it changes signs to positive, equals, and here's where I'm going to pull out my y prime. Y prime times the quantity of negative 12xy squared minus 6x cubed y squared. And now I can divide both sides by negative 12xy squared minus 6x cubed y squared, so that I isolate that y prime. Now, there is going to be some simplifying I can do, because do you recognize that every piece, every term here, the 4, 4, 6, 12, 6, the common factor is going to be 2. I can't divide out any x's or y's, but I can divide out a 2 from everything. When I divide everything by 2, you could do that intermittent step of factoring the 2 out and writing what you get when you factor. Let me show you what I mean with that, just in case you're not sure here. It would be 2, and then 4 divided by 2 is 2. 4y cubed divided by 2 is 2y cubed. 6x squared y cubed divided by 2 would be 3x squared y cubed. So you could do that factoring first and then do the same thing to the denominator. 2 times negative 6xy squared minus 3x cubed y squared, and then I can divide out those 2's. You might not feel like you need to show that step, and that's fine also, but here's what it would look like when I divide everything by 2. In the numerator I have 2 plus 2y cubed plus 3x squared y cubed all over the denominator negative 6xy squared minus 6x cubed y squared. And the only thing I could do to simplify this, it's a little bit better format to put this in descending order. So I'd really want to put this 3x squared y cubed first, because that's 5th degree. And then the 3rd degree term plus 2y cubed, and then the constant 2. And same thing in the denominator. And also I could factor out a negative here and have negative 6x, so take the opposite, and then it's 6x cubed y squared plus 6xy squared. I'm going to look at this one more time. You know what I'm noticing is that I think I made a little mistake somewhere. Let me go back here, because I know this should have been 3. Now, I won't lie and say I did this on purpose, but I will say it's a great opportunity to demonstrate that you always want to go back and double check before you write the final answer, right? And here I can see clearly that when I divide by the 2, I should have written that as a negative 3 x cubed y squared. So let me go ahead and correct that now. I'll just erase that and rewrite it correctly with that 3. Hope that didn't throw anyone off. But that gives us our final correct answer. And that's why when I print these examples, I like to show the possible answers. And you can see that you could have double checked. If you had done this problem, you hopefully would have found your own mistake also. But that's example 5. Let's move on to example 6. Now to do 6, I'm going to erase this part of the bottom just a little bit. We're going to continue using implicit differentiation and chaining. So watch what's going to happen with this term on the left. When I do the chain for this quantity squared, when I do that derivative, I've got to be mindful of chaining and thinking through the derivative of the outer function is going to be 2 times this thing that's inside the bracket to the first power, right? And the thing that's inside the bracket is the 4y squared plus 3. And to chain, I'm going to then go back and say times the derivative with respect to x of 4y squared plus 3, which is 8y and then the derivative of the 3 is 0, right? And then I've got to still catch that I've got to do the derivative of y. So whenever there's a y term, I'm going to be really thoughtful about remembering that I'll need to chain. So the derivative of 4y squared plus 3 quantity squared with respect to x is going to be 2 times that quantity, 4y squared plus 3, times the derivative of 4y squared plus 3, which is 8y, times the derivative of y, which is y prime. The right side comes up much easier because we just have the derivative of 4x cubed, which is 4 times 3 is 12, x squared, times the derivative of x with respect to x, which is just 1. To solve for y prime, I am going to subtract the 2 times the quantity of 4y squared plus 3. Oh, wait, sorry. Let me look at this again. I've got to simplify this first before I go dividing out. So let me do that. when I simplify this, I'm going to have 8 y squared plus 6 times 8y times y prime equals 12x squared. And then I've got to distribute the 8y also. You see how much algebra is involved here? It really is the case that most students who make a mistake, they're not making a mistake with the algebra or with the calculus. It's usually with the algebra. But I could do a couple of these steps together. So I could say I'm going to divide out the 8y squared plus 6 and divide out the 8y to solve for y squared. I am still going to need to simplify that though. Eight y over 8y is 1. 8y squared plus 6 over 8y squared plus 6 is 1. So I get the y prime is equal to 12x squared over this product. Now, do you see what we could simplify? Because these are both multiplied, I could divide 4 into 12 to get 3. 4 into 8 is 2. And now I'm going to distribute this 2y. So 2y times, let me write out what we've got here. We've got in the numerator a 3x squared. In the denominator, we've got 2y times 8y squared plus 6. Oh, and actually, we could leave it in that factored form. There's no reason to multiply it through. And you will find that answer in the answer box. Multiplied out. But you could, if you were doing this on your own, there'd be no reason to have to simplify this, to have to multiply it through. You could leave it factored. But if I do multiply it out, we'd have a 3x squared and then 2y times 8y squared, 16y cubed, 2y times 6 plus 12y. Don't get caught into this trap of thinking, I can divide the 3 and the 12. You can only divide them if the term is a factor, right? If it's a factor, not if it's a term. So that's it for number 6. Let's try this last example on the page, number 7. Secant of y to the 9th equals 5x squared plus 2. If I'm doing the derivative with respect to x, then I'm going to do that derivative to each term. Now the derivative of secant, because what I'm going to think of is secant, tangent. That's just such a nice way to memorize. The derivative of secant is secant tangent. So when I do the secant of y to the 9th, I'm going to have 3 factors. So make sure you're ready to chain. So the derivative of the outer function is a secant. The derivative of secant is secant tangent. So the first piece I get for the derivative of secant of y to the 9th is secant y9 tangent y9. And then I've got to chain that y9. So times the derivative with respect to x of y to the 9th. And that is 9 times y to the 8th. But wait, there's more. So then I have to do times the derivative of y, because that y doesn't match up to what we're doing the derivative with respect to. So the derivative of y with respect to x, I'm going to write as y prime. The other pieces are going to be pretty easy to do the derivative of. The derivative of 5x to the 6th is just 5 times 6 x to the 1 less than 6. And the derivative of 2 is just 0. You don't even have to write it. Now I'm going to solve for y prime. So I'm going to say y prime is 30x5 over, I'm going to pull that green 9y to the 8th up in front. So 9y to the 8th times secant tangent. Secant y to the 9th times tangent y to the 9th. And you should find that answer right here. Almost. You see that we could reduce still by 3. 3 goes into 30 10 times. 3 goes into 9 3 times. And now we've got our final reduced answer. Well, I hope this video has helped you with these 3 examples. I know they're not easy, but they're certainly doable.